Hello everyone. This project aims to evaluate how reliable large language models are when applied to a biomedical task and to provide a transparent, fully reproducible framework for comparing different models. The background is large language models are being used more and more in biomedical research. Things like question answering, clinical reasoning, and extracting disease entities from text. However, even though these models are powerful, their real-world reliability in the biomedical domain is still unclear. Many existing evaluations use different prompts, different text lengths, or inconsistent pre-processing steps. These differences make comparison unfair and result difficult to produce. To address these problems, we create a standardized, reproducible benchmarking pipeline that evaluates three major biomedical NLP tasks in zero-shot mode, while keeping tokenization, truncation rules, prompts, and the evaluation matrix completely consistent across different models. So the dataset we use is three widely used biomedical datasets, and the first is the PubMed QA. This evaluates the factual understanding. Each example includes biomedical research questions and abstract, and the model must answer yes, no, or maybe. And second is the MedQA. This tests the clinical diagnostic reasoning. These are four option multiple choices questions based on the topics, and they require multi-step reasoning, not just the pattern matching. Third is the NCBI disease NER datasets provide token-level disease annotations using the standard BIO tagging scheme. This evaluates how well a model can recognize disease mentioned inside the biomedical abstracts. So the method, we designed a three-layer pipeline. The first, the data loading and pre-processing. So all data sets are standardized through the same steps, tokenization, controlled truncations, and also the consistent prompts templates. For the NER text, we also remap entity labels to ensure alignments with the model's output format. Second is the model inference. We test three models that represent three different model families. So all models run strictly under zero-shot settings, which means there is no pre-train. We also standardize max token length, padding positions, decoding strategies, and the batch generation, ensuring the comparison is clean and reproducible. The final evaluation, each model is evaluated using accuracy for QA task and the F1 score for NER. Because all pre-processing steps are ununified, differences in performance generally reflect differences in model capability, not differences in pipeline design. So the result based on our experiments, we observed several important findings. For MedQA US, for PubMed, the general model clearly outperformed the BioGPT. This matched recent research showing instruction-tuned models are better at general reasoning and evidence interpretation. For MedQA, the boost model struggles, which is expected because clinical MCQs require strong domain-adapted reasoning. BellGPT performs slightly better here, but accuracy remains low for both models in the zero-shot settings. We also found that BellGPT large shows instability. In PubMed QA, its performance fluctuates significantly depending on the text length, showing signs of factual drift when processing longer biomedical passages. For the NCBI disease NER task, biomedical NER all achieved the FA is 0.449, which is far below typical fine-tune benchmark. From zero point 0.6 to 0.85, this revealed the strict zero-shot NER is still far from practical deployment and require dataset-specific training to perform well. Overall, this result highlighted domain-trained models are not always more robust, and that zero-shot performance alone is not reliable for biomedical tasks that require high precisions. So our conclusion shows the biomedical language model performance vary heavily across different task types, and relying solely on zero-shot inferences is risky for clinical or scientific use. Instruction tool models like FLAN-T5 excel at reasoning, while specialized models like PyGPT do not always outperform general models. Our, our reproducible pipeline provides a stronger baseline for evaluating future biomedical LLMs in a transparent and standardized way. So that's it.